So this is what a classic implementation might look like. We start off with our laser. It moves through a phase modulator. Don't worry, if phase and frequency modulation are essentially the same thing. So if you're modulating your laser frequency, it's analogous. The phase modulator, you can think of this as imprinting phase sidebands on the carrier, and we'll look at that a little bit later if you're not familiar with that. Then these three fields, the carrier and the two sidebands, incident on the cavity, using polarization tricks or just a beam splitter, we get light onto a photodiode. Now this photodiode, it doesn't detect the field, it detects the power. It's a diode detector. The hint is in the name, and that's important too. Then the output of the photodiode goes to a mixer. A mixer is just a multiplier. So one port of our multiplier or our mixer is our photodiode signal, and the other port is the same waveform that we used to create our sidebands. So if we send a 10 megahertz sine wave to our phase modulator, that's the same signal, 10 megahertz sine wave, that we send to this mixer. There could be some phase shifter in between. That could be cables or a dedicated phase shifting board or instrument. But that's what happens. Then the output of the mixer goes through a low-pass filter, and that is your Pound-Drever-Hall error signal at this point in the loop. We can then use a servo to feed back to the laser and steer and hold the laser on resonance with the stable cavity. But what's really going on here? So we have the carrier and the two sidebands from coming out of the phase modulator. Around resonance for the carrier, the two sidebands are just reflected onto the photodiode, whereas the complex response of the cavity is imprinted onto the carrier. And then on the photodiode, we look at the beat between these fields. That's what's plotted here on the inset of this graph. We've got the beat note on the photodiode as we move through resonance. And you can see here, it's very similar actually to the dither locking. We're doing phase sensitive detection. The difference being we're at a sort of different corner of the parameter space in terms of modulation depth and modulation speed. So we have a beat note oscillating at the modulation frequency, and you can see it gets bigger. There's a strange phase flip, and then it gets smaller. So if we demodulate that, if it goes through our mixer and our low-pass filter, what comes out is this orange trace. This is our Pound-Drever-Hall error signal. And you can see I've got the transmitted power from this photodiode here on the graph too. And you can see it lines up nicely. Some advantages of Pound-Drever-Hall is that unlike the dither locking, it doesn't broaden the line width. Unlike the side of fringe locking, it has a wider capture range, and noise in the power of the laser is okay. Also, because we're operating at high frequency, say 10 megahertz, usually it's some number of megahertz, we really only care, at least before demodulation, about noise at that frequency. So it's very easy to get good performance. Disadvantages, you see there are several components here. So it can be quite complicated, and if you're using legacy equipment, it can be a little bit expensive. But digital hardware can help in this case, bringing everything into one box and making it a little bit more economical. So lots of ways to lock cavities. They all have their pluses and minuses. It really just comes down to what's the reference. Is it some voltage or sample of the laser, like side of fringe locking? Is it sidebands like PDH? Is it a polarization mode or a higher order spatial mode, like some of the other techniques? But if you asked me, how should I lock my cavity? If I didn't know anything about what you were doing, I would just say use PDH. It's the vanilla, the default, the kind of industry standard technique.